Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
All right. Welcome everybody to today's AI for Good webinar. I'm Alexander Winkler from the Max Planck Institute for Biogeochemistry and the LS Unit Vienna, and I will be moderating today. I'm very happy to welcome today's speaker, Marieke Wesselkamp. Marieke is a doctoral student at the University of Freiburg within the Department of Biometry and Environmental System Analysis. She holds a bachelor degree in geography and a master degree in environmental sciences, where she focused on process-guided transfer learning with sparse data. Since 2023, she works on developing machine learning-based emulators for the land surface scheme in the IFS model in collaboration with the ECMWF. In that, her main interests are exploring the potential and limitations of theory-informed machine learning for seasonal forecasts and the role of land surface states. Today, she will talk about how to develop robust surrogate components of land surface states for hybrid Earth system models. I'm very much looking forward to your talk, Marieke. Please go ahead.
Thank you for the introduction, and thanks for inviting me. I'm really happy to get the chance to present my research in the context of the Seminar for Earth and Sustainability. What I will talk about today is basically overviewing my PhD project. Much of the work I did focused on the integration of physical models with machine learning approaches, and all of this at case studies that concern the natural land surface of our Earth system. This is a topic I find specifically relevant in the global context from a sustainability perspective, as Earth system models play a significant role in gaining knowledge about future climate and weather dynamics. Before I'm going to say anything more, I quickly want to lose some additional words on my background. As Alexander said, I'm doing my PhD in Freiburg, a small town in southern Germany. And since 1.5 years, I'm regularly visiting the European Center for Medium-Range Weather Forecasts, mainly the headquarters in Reading. From Freiburg, we also have a collaboration with the University of ECLand. So I want to thank all my collaborators on these projects in Freiburg, ECLand, and in Reading. I present our projects today under the title Towards Robust Surrogate Components of Land Surface States for Hybrid Earth System Models. In part, I also like to think of our work as towards physically consistent machine learning models of the land surface. Now, mostly when we talk about surrogate models, we refer to a type of statistical or deep learning model that replaces or emulates a specific component of the larger Earth system model. These AI models will be the central players of today's talk, centered around a land surface emulator that we call ECLand. The reason why this is interesting for a larger community is that compared to the numerical model scheme they replace, machine learning-based surrogates usually have a much better runtime as they are trained. They allow for quick experimentation regarding research questions. They can be fully differentiable by design and are flexible to extend or recalibrate. Some downsides of their application are that they might not represent the known physical laws consistently, which can lead to unstable interactions in coupled simulation. They can show unrobust behavior out of their training samples, and initially they still represent black box processes for us from a scientific perspective. With our project and in today's talk, we will address some of these advantages and disadvantages, all at the example of land surface processes. So before I give an outline of our projects, I want to give a background for their context. When we look at the representation of the land surface in the global physical Earth system from a model perspective, we can do this in a hierarchical way. Because I work with meteorologists, I assume an Earth system model and atmospheric model. In the atmospheric model, the atmosphere is layered, and on the lower level is where it interacts with the surface of the globe, that is the land surface. The land surface for a long time has just served as a boundary condition for the atmosphere, but is now increasingly represented as an own model component with feedbacks to the atmosphere. These feedbacks happen two ways. The atmosphere forces the land surface fluxes, and these forced land surface fluxes are transferred back to the atmosphere. These fluxes are averaged from tiles over a grid box, of which we are looking here only at fluxes happening on tiles of the natural land surface. Within such an Earth system modeling framework, subgrid processes are traditionally represented by physical laws and numerical schemes. Now, lately, data-driven components are increasingly used to correct, extend, or improve smaller or larger components. As data-driven models become an integrated part of the Earth system modeling pipeline, we like to call the resulting scheme hybrid model. Now, the scheme I'm showing here is adjusted based on a review from integrating data-driven and physical models in hydroclimatic forecasting. And I want to use it to define what we understand as a hybrid forecasting model. It classifies hybrid models into statistical, dynamical, serial, and coupled approaches. And to the author's classification, I added extended, which refers to a combination of any of the above. In statistical dynamical approaches, a data-driven model is trained on hybrid datasets. Now, datasets along a gradient of simulations and observations in input and output or target data. This approach incorporates emulation, pre-training, and transfer learning. In serial approaches, involve running a data-driven model for pre- or post-processing of input or physical model predictions and are used for corrections on either side of the pipeline. And coupled approaches run the physical model or the data-driven model conceptually in parallel or couple them by simultaneous optimization of the data-driven component or parameter calibration of the physical model. And as I mentioned, then extended approaches combine any of these. So on one hand, we understand hybrid forecasting as physical forecasting with data-driven components. Hybrid machine learning takes place on the scale of the physical model or refers to the whole forecasting system. On the other hand, there is the field of physics-informed machine learning that comes from the inverse perspective. Here we focus on data-driven modeling or forecasting with physical information. The research on physics-informed neural networks happens on the scale of the data-driven model, where physical information is supposed to inform the neural network. So the field of physics-informed neural networks and of hybrid machine learning can be seen as two paradigms across a data-driven and theory-driven modeling gradient. However, they also overlap to a certain degree, and they are not exclusive. On one hand, process of physics-informed machine learning components of hybrid forecasting systems can help enforcing physical consistency. On the other hand, a machine learning surrogate that learns from the physical model online or coupled to a physical model over multiple integration steps can improve in robustness. However, only few people go the whole way to online learning, and even though I did a long introduction until here, we did not. But this provides the background within which we conducted our studies. So within this context, we will look at three different projects that we conducted throughout my PhD. In the first part, we will explore how process-based models can inform data-driven models, such that not only predictions are improved, but that we can explore how hybrid models represent our physical processes. In the second part, we will explore the advantages of selected data-driven models in emulating a physical land surface model scheme on the large scale. And in the third part, we will explore the robustness to apply these data-driven emulators to observations. From a physical Earth system perspective, the land surface is where land-atmosphere exchanges happen in the form of meta-energy, water, and carbon fluxes. It couples the biogeochemical system to the physical climate system. And in each part of this talk, we will be concerned with one of these fluxes. To start with, we will look at how process-informed neural networks improve predictions and inference. So what we did in short was we created a selection of hybrid neural networks. We benchmarked their performance against a process model and a naive neural network, and we inferred process representation in these hybrid models. We do not run our experiment on the physics-informed neural networks, but process-informed neural networks. This is on one hand because our model is not a physical model, but a semi-empirical process model. On the other hand, this is because we do not want to overstate the approaches here. Physics-informed approaches, as they have been defined by Kaniadakis et al., impose stronger constraints by hard-coded equations in the data-driven model structure. That said, in this experiment, we don't forecast, but we train our models to estimate carbon fluxes as a point process, and then we use this model to extrapolate in time to unseen data. The process that we focus on is that of light use efficiency in boreal forest ecosystems. Light use efficiency models the carbon exchange, which is represented by the gross primary productivity, short GPP. GPP is basically the biomass production in ecosystems, here in boreal forest ecosystems. The process-based model that we're using is the simple and semi-empirical process model PRELIS. The core of PRELIS consists of 3 coupled time-discrete equations, and beyond gross primary productivity, GPP, it also predicts the evapotranspiration and the soil water content. GPP is a variable that is strongly determined by the yearly cycle. The production of biomass in forest ecosystems happens much during the summer and stagnates in the winter. We are comparing 5 approaches of process-informing neural networks. And while all of them eventually target the gross primary productivity, GPP, they vary in the training protocols, the input and target data used, the loss functions we constructed, and the model structures. We conducted a main adaptation that is a specific transfer learning approach where the data-driven model is pre-trained on an artificial database and a subsequent fine-tuning to observations. We constructed a bias correction, which is the post-processing step, where the physical model is run to generate predictions and a neural network is used to correct between physical model predictions and observations. We compared 2 different physical loss functions, as we call them, one where we term parallel physics, where we optimized on the average neural network and physical model predictions, and one that we term physics regularization, where we optimized on a combined loss function with a regularization parameter. And finally, we conducted an embedded calibration where forward and backward passes during optimization are propagated through the physical model. This allows us to optimize both the neural network and the physical model parameters simultaneously. And at this point, I want to acknowledge that along much of the other work, this specifically is the pet topic of the first author of this work, Niklas Moser. He's currently doing his PhD at the University of Jyväskylä in Finland in the lab of Otto Overskainen. With all these process-informed neural networks, we conducted multiple prediction experiments. And here we see the results from a temporal prediction. Models were trained on 4 years of data just of one site in Hiittala in Finland and evaluated on 1 year. We trained them in a temporal block cross-validation, and this is what the uncertainty bands of the box plots on the left-hand side indicate. Benchmarks here are the process-based model in yellow and a pure data-driven model that is the naive neural network in pink. The best performing model is highlighted with a star, that is here the parallel physics neural network. In this example, we found that most data-driven approaches outperform the physical model. The parallel physics and the regularization models even outperform the naive neural network on average. Why this was surprising for us is because the naive neural network is fully unconstrained and potentially capable of fully representing the information in the data. We interpret these findings such that training towards physical model predictions provides information that is missing or covered in the training data. In case of the parallel physics neural network, constraining the loss function by physical model predictions forces the data-driven part to fit the residuals based on the input data. We then looked into how neural networks represent the process model information by conducting a conditional variable importance analysis. This means we explored the effect of all input variables to the process model and the neural network models on the model prediction of GPP, the gross primary productivity. So the input were 5 dynamic variables: temperature, vapor pressure deficit, rainfall, the photosynthetic active radiation and the fraction of it absorbed by the canopy. We have the GPP here on the y-axis, the gross primary productivity. Now, to reduce information, I only want to look at two of them. That is the photosynthetic active radiation and the fraction of this radiation absorbed by the canopy. We varied input variables that are the input variables to the process model and also the input variables to our hybrid neural networks. We varied them along their full ranges, which we see here on the x-axis, standardized, and the predicted GPP is displayed on the y-axis. Now, the solid lines indicate how these variables are represented functionally in the respective model. The uncertainty bands show the variability within a certain time period. Here we're looking at the end of the growing season in June. In yellow, we see how the variable is represented in PRELIS. For the photosynthetic active radiation here on the left, we see that it is represented non-linearly in PRELIS, and the fraction of absorbed photosynthetic active radiation by the canopy is represented as a linear function. And now in red and purple, we can compare the functions that, for example, the parallel physics in red and the naive neural network in purple fits. The parallel physics neural network was our best performing model in this scenario, here displayed in red. And what we see is that it is making strong corrections. For the fraction of absorbed photosynthetic active radiation on the right-hand side, it fits an inverse trend to PRELIS. The naive neural network, the MLP, without a process guidance, fits a similar non-linearity as PRELIS for the photosynthetic active radiation, but a reduced trend for the fraction of it absorbed by the canopy on the right-hand side. As these statements kind of align, we can hypothesize the following. The effect of radiation absorbed by the canopy may be overrepresented in our process model for this specific time and site. But to conclude, this would need further research. Now, to conclude on this first project, we can use physical information to guide the data-driven model towards our theory, which can lead to better predictions. Now, training towards the process model may also be useful to locally correct for model misspecifications. However, which of our introduced approaches is best depends on the application and on the size of the process model. Now, with this in mind, we move on to the second project. In the second study, we created ECLand, that is a machine learning-based land surface emulator. What we did in short was we created a database from physical model simulations, that is here from ECMWF's land surface scheme ECLand, and from reanalysis forcing data. We developed a selection of machine learning models that we trained on this partly synthetic database, that is, we emulated the physical model. We verified the emulators as alone standing forecast models against numerical model predictions. While we looked at the prediction of carbon fluxes at point processes before, we are now going to look at forecasts of water and energy fluxes on a large spatial grid. We use different data-driven approaches and a completely different physical model. This project happened in close collaboration with the ECMWF, the European Centre for Medium-Range Weather Forecasts. As such, we are looking at the example of the numerical land surface scheme of their integrated forecasting system, short the IFS. The land surface scheme of the IFS is ECLand, which parameterizes the boundaries and initial conditions of the IFS. ECLand exchanges with the atmosphere via skin temperature that is parameterized by an energy balance equation. This equation is solved in the lower layer of the atmospheric model. The energy balance is computed from a range of prognostic land surface states, and among them are soil moisture and soil temperature at 4 different layers and snow density at multiple layers. We will look at snow density as an aggregated variable, that is as the snow cover fraction on the surface, and at 3 soil layers. These and more prognostic land surface states modulate the variables of the energy balance equation. ECLand is refined in the processes that drive these states that are related to vegetation and hydrology, disturbances, and urbanization. Within this forecasting scheme that we already know, we are now working again in a statistical dynamical setting. Even though technically we do not speak of emulators and hybrid models, they are parameter informed by the physical model. Further, they provide a basis for coupled approaches if the goal is to move from a purely physical machine learning based from a purely physical to a machine learning based parameterization. In our approaches, we constrain the emulators towards the physical model by optimizing on the incremental changes in a rollout manner. These incremental changes are basically time derivatives of the state variables, that is, their first differences. This is also how the physical model computes the time evolution of prognostic land surface states. We compared 3 machine learning emulators. That is an extreme gradient boosting algorithm, a discrete decision tree ensemble learning algorithm, a multi-layer perceptron, that is a fully connected neural network, differentiable, and a long short-term memory neural network that is also differentiable and time explicit, short LSTM. We designed the LSTM here as an encoder-decoder model, where the encoder model is trained to initialize the decoder, and the decoder is trained for forecasting. All of these models target 7 land surface states from ECLand simulations. That is a synthetic dataset. The total of 41 input variables are ERA5 reanalysis data and ECLand simulations. Reanalysis data are observations that were simulated with the IFS and as such not purely artificial. The input that we call X here is static information, that is so-called climate, that we call climate fields. This is environmental parameters which vary only in space. The other part of the input that we call Y here is dynamical meteorological forcing. That is information that varies in space and time. And then there is the historic states of the land surface simulated from ECLand. We developed our model on a high resolution European scale at 31 kilometers and trained the selected model structures also on a lower resolution global scale and 100 kilometers. The training period was 2010 to 2020, that is 10 years at a 6-hourly resolution. In the following, I will focus on the high resolution European models because we spent more time with them after development. I will refer to all of these models together in the following as ECLand. Before looking into the forecasting performance of ECLand, I want to give a glance on their runtime. After training, the evaluation of either of the models run with a significant speedup in runtime on computational resources, while the physical ECLand scheme takes 240 minutes, that is approximately 4 hours, to evaluate a full test year on 16 CPUs on a Linux machine. XGBoost takes approximately 5 minutes, the MLP seconds, and the LSTM 3 minutes. So the slow runtime of the LSTM compared to the MLP is caused by a spatial chunking procedure that we did not optimize for this work, but can certainly be improved in the future. Now here we see the forecast from for 7 land surface states from all of our models over the test year 2021. Models were initialized on January the 1st. This shows more than 1,400 lead times at 6-hourly resolution, that is over 1 year. The top row shows soil moisture at 3 layers of depth, the medium row soil temperature, and bottom shows the snow cover fraction. ECLand dynamics are shown in black and the emulators in green, yellow, and light blue. This is a good example grid cell. It is the grid cell with a minimum root mean squared error for the LSTM. Now what we see looks nice. The emulators can really approximate the dynamic of the physical model and even captures daily cycles. However, we also see some physically unrealistic predictions. The MLP, for example, predicts a negative snow cover fraction, which is physically impossible. While we could detect this inconsistency for the snow cover here, we did not, for example, test for the water balance. This would allow us to test inconsistency in soil moisture forecasts, but this is currently not achievable as the emulators do not predict all the required state variables. Now, when looking at the scores aggregated over all lead times, grid cells, and variables, we found the highest averages and median scores for the LSTM. The root mean squared error and mean absolute error are declining scores, and the anomaly correlation, short ECC, is bounded between -1 and 1. Now, being aggregated over all variables, RMSE and MAE are not directly interpretable. But for a direct interpretation, we can look at the ACC. The ACC in our case makes the statements about the correlation of forecast model error and physical model error towards the expected long-term mean. An ACC of 1 indicates a perfect correlation and an ACC of 0.5, a forecast model error similar to that of the physical model. All of our models have an ACC of 0.7, that is the high correlation of ECLand and ECLand errors. Further, we found that the in root mean squared error, the LSTM showed an improvement of 30% towards XGBoost. And the MLP showed in general the lowest variability in root mean squared error and mean absolute error. Looking into the scores at the variable level, the results look a bit different, and for soil moisture even diverging. Here we see that the RMSE for soil variables in the first layer and the snow cover fraction on the surface. Now, XGBoost achieved the best scores for soil moisture and LSTM for soil temperature and snow cover. This is largely representative also for the deeper soil layers, just that XGBoost also improves for soil temperature forecast at deeper layers. Our interpretation of this divergence in total and variable level scores is that the snow cover dominates the total scores, as we computed error metrics on non-standardized variables, but I'm happy to learn more about potential interpretations. We then ran our first experiments with ECLand as a standalone land surface model. We looked into the predictability of land surface states as represented by ECLand. We explored forecast horizons with the anomaly correlation, the ACC, on smaller spatial regions in this example of southern Scandinavia. The ACC quantifies correlation of the AI model and the physical model error, our ground truth. An ACC of 1 indicates perfect correlation, and below 0.5 that the AI model forecast has no value compared to just forecasting with a long-term mean. We computed ACC over lead times from different initialization times here on the x-axis. The diagonal structures in the heat maps indicate a temporarily consistent system error. This can be interpreted as physical limits of system predictability, where the initial forecast time does not affect forecast scores anymore. In contrast, vertical structures indicate a systematic model error that appears at specific initialization times and that is independent of initial forecast date. This we see, for example, for XGBoost when starting the forecast in summer. What we here learned, for example, is that the multilayer perceptron performs consistently more independent of initial forecast time, most consistently. All models have difficulties, though, to predict the seasonal change in May when we start the forecast in winter. And the LSTM specifically seems to have difficulties, at least for some grid cells, as is visible in this horizontal structure that we interpret as a failure of predicting snow melt. Now, to conclude on this study, with all of our models, we could achieve a significant speedup of evaluation runtime. Our models represent the physical model dynamic on the long range. For some cases, at the examples of snow cover, however, we saw that more physical constraints could improve consistency. We got overall good total scores. Which model, however, is appropriate is again application specific. And after validation, ECLand can serve for standalone experimentation, which we demonstrated already as our predictability experiment. And with these findings, we come to the third experiment. And here we applied ECLand as we just developed it above to another data domain and quantified its forecast horizons on observations. Now, what we did in short was we used an observational database with ground station soil variables, that is the International Soil Moisture Network. We initialized ECLand with the station data and then evaluated its forecast at these observations with empirical forecast horizons. Here we are again using our developed forecasting models and use them now to forecast at specific point processes that are matched with gridded forcing as input data. This experiment validates our developed models, and at the same time, we can conduct another standalone predictability experiment. We're using the 3 exact same models that we've just developed, more specifically the models developed on the European scale. That was an extreme gradient boosting algorithm, a multi-layer perceptron, and a long short-term memory neural network. All received the same input data, that was 41 input features consisting of static environmental parameters, dynamic meteorological forcing, and dynamic land surface states from physical model simulations. All of them target 7 land surface states simultaneously, that is soil moisture and temperature at 3 different layers, and aggregated snow cover fraction. We're using observational data from the International Soil Moisture Network database. This database contains local soil measurements at multiple soil layer depths. More specifically, we use station data from network stations in southern France. That network is called Smosmania. These measurements then initialize ECLand instead of the ECLand simulations as in the preceding experiment. With this information and the ERA 5 forcing at the respective station, these models now forecast land surface states over all lead times. We evaluated the robustness of their application on the soil station data by quantifying the empirical forecast horizons regarding the station data observations. We did this in absolute terms and in relative terms relative to a non-initialized physical model, ECLand. In doing this, we run all models separately, but we evaluate ECLand here as a model ensemble. This might seem uncommon with only 3 models, but we inspected the uncertainty beforehand. This can be inferred from 3 data points from the model ensemble variance under normal assumption with a scaling factor of 4.3. Before showing the results, I want to introduce the empirical forecast horizon. Quantifying a forecast horizon is one way to measure predictability. The empirical forecast horizon is defined as the moment in time at which a scoring function falls below a predefined tolerance towards this score. As such, for the computation of a forecast horizon, we need a scoring function, a tolerance towards the score, and a reference for forecast evaluation. For our experiments, we choose the mean absolute error as a scoring function, a tolerance of mean absolute error towards that function of 1.5 Kelvin, and as a reference for evaluation, the soil station data from the International Soil Moisture Network. This, together with ECLand as benchmark for computing the skill, gives us the relative and the actual forecast horizons of ECLand. We found that the medium range is an appropriate length to evaluate for soil temperature. Here we see the forecast in the left-hand column, the forecast of ECLand, of ECLand, and the Smosmania network stations in green. We see the actual forecast horizon in the column in the middle, and we see the relative forecast horizons in the right-hand column. The relative forecast horizons, also known as the forecast skill horizon. Here I want to focus on the results of the relative forecast horizon on the right-hand column. On the y-axis, we have the mean absolute skill score of ECLand towards ECLand. Skill is a relative score of the AI model towards our physical model. With a skill, such as skill is defined with a skill of 1, the AI model is perfect, and as it drops below 0, it is no better than the physical model. In our plot here, the dashed horizontal line at 0 indicates the threshold at which ECLand loses all skill towards ECLand. As such, the decline towards this threshold indicates the loss of information from the initialization of ECLand with the soil station data. What we are interested in is the lead times where the following is happening. We're interested in the lead time at which the mean absolute error skill score drops below 0, that is the relative forecast horizon. This is the moment in time where the AI model is no better anymore than the physical model. As such, this is the moment in time where the information of initializing ECLand with the observation is lost and where ECLand approaches again what it has been trained on, and that is the physical model. Because it is easier to overview, this summarizes the information. For the relative forecast horizon, we look at the purple box plots. The uncertainty bands of these box plots indicate the variability among stations. With observations as initial states, ECLand has an advantage over ECLand of a time horizon of 12 hours on the surface layer, that is 2 time steps at 6-hourly resolution, nearly 2 days on the subsurface layer 1, and 16 time steps, that is 4 days on subsurface layer 2. Our interpretation is that we here have an increasing memory of initial conditions towards the lower soil layers, and that is an increasing predictability. This memory is even stronger for soil moisture. Here we evaluate emulators for a range of 2 months on the seasonal range. And beside, on the surface layer, we see that relative forecast horizons here extend beyond the seasonal range of 2 months. For soil moisture, however, this is not a completely fair comparison because usually the physical model is bias corrected before evaluation. A conclusion from this analysis, however, could be then that this bias correction is becoming obsolete for ECLand. Now to conclude, what we found is that ECLand is quickly initialized with data from a different domain, offering more flexibility than a physical model. This could make a bias correction as required for a physical model obsolete. ECLand shows robust behavior and forecast in the observation domain. However, information in the observation domain vanishes more quickly for quick processes on the surface layer, with assumingly lower predictability. And this memory is longer for slower processes on subsurface layers. Now to summarize, we looked into how process-informing neural networks can improve prediction and how we can infer process representation. We developed a selection of emulators that can forecast multiple land surface states simultaneously on the large scale. And we applied these emulators to another data domain that was the soil station measurements, and we inspected their forecast horizons. By now you have maybe forgotten about the long introduction I gave, so I want to synthesize. By looking into process-informing neural networks, we opened the black box a little bit. This allowed us to infer knowledge about process representation in these hybrid models. And while we focused on the correction towards the physical model, this also allows us to inspect if the functional representations are consistent with the process model. We looked into the development of 3 land surface emulators that successfully represent and forecast the dynamic of our physical model scheme on the large scale. We found that all of them significantly improve runtime towards the physical model scheme. In large parts, they reproduce physical model dynamics at long lead times, however, still with some physical inconsistencies. We illustrated how they can serve as standalone models for quick experimentation on the land surface. And as surrogate components for the physical core, neural networks have the advantage of being differentiable. That is a topic that we did not into, but this can be useful for coupled data assimilation. We applied the emulators to a new domain and explored their robustness to a domain shift. We found that this robustness likely depends on the predictability of the variables. The models that were trained on the artificial data showed a short memory for new information on quick variables on the surface layers and a longer memory for slow variables on subsurface layers. Now we presented or developed ECLand as a alone standing land surface forecasting model. ECLand, however, is still incomplete in the representation of the land surface variables. So one direction in the future is to have a machine learning model that represents a full land surface scheme. Another direction to go is developing ECLand more towards a machine learning model for the parameterization of the Earth system model. While these 2 goals will focus on different developments, they will yet profit from each other. If surface energy balance should be met for coupling with an atmospheric model core, for example, all these components need to be represented. And this will then allow us for testing physical consistency and hence provide a consistent parameterization. How far it is useful to employ physical constraints is yet an open question to us. We did not go as far as to combine the 3 projects in that we did a transfer learning of the standalone model schemes on the soil station data that we had with potentially physical loss functions. Now this will be for the future because it was beyond the scope of my PhD. And with this, I'm already finished talking. So I want to thank you all for listening. I want to thank all my collaborators on these projects, my co-authors, and many more people from helpful discussions with which I profited. If you're interested in our work, I invite you to check out our articles that I listed here. And now I'm open for questions, and I will try to answer them as best as possible.
All right. Thank you so much for this wonderful talk. So while we are waiting until the questions come in, I might start maybe with the first question for you, and that speaks to the first study that you presented. So maybe you can elaborate again a bit on this aspect that you had this naive machine learning model that seemed to be more physical than actually the model that had parallel physics, where GPP. So maybe you can also elaborate on this aspect again.
Yeah,
maybe
yeah.
didn't
Maybe
fully
I show the results again.
Yeah.
Yeah.
Because there you had this, so GPP decreased with increasing fraction of absorbed radiation in the parallel physics model, and the naive one, it basically got it got I would say a physical plausible response. So could you elaborate again?
Yes. Yes, that is in the nature of the approach of this parallel physics model. So I'm not showing this here, but maybe you remember that in the loss function, we optimize on a combined term of the process model and the neural network predictions. And this forces the neural network to fit the difference between the process model predictions and the observations. So in a sense, this also corrects the residuals of physical model and observations. And this is the correction that we see. That is why we have an inverse trend here.
Okay.
This is not making the absolute predictions.
Okay, I see. Thanks for clarifying.
Yeah.
All right, then we have a question coming in from Carlos Ruiz Gonzalez, and he asks, how is the structure of the MLP that predicted negative snow? Couldn't one just bound the outputs with a different final activation?
Yes, that is correct. I'm also going to show the results again here. That was concerning this plot.
Yes.
Yes. We also discussed about this because that is obvious. We could have actually bounded this output with a ReLU, for example. I think we also did this before, but I was interested actually in the raw presentation of the processes, also compared to the XGBoost and to the LSTM. But this is definitely a good suggestion. Thanks.
All right. Then I would have another question. So when you created these emulators for ECLand, did you also consider plant functional types? Are they actually in ECLand? And would you say it is needed to have, or is it important to have them for now processes that you modeled?
Yeah, that's also a good question. So I noticed that I didn't really show the input data to these emulators, but we can maybe have a look at the database together. So plant functional types are represented in ECLand. We do not explicitly have them in our model. Actually, we have the type of vegetation, if it is low or high, and specific vegetation parameters for low and high vegetation, but not specifically the plant functional type. So right now, ECLand also obviously predicts GPP, for example, and the carbon fluxes. Our emulators right now do not predict the carbon fluxes. I would definitely consider including them for the carbon flux representation. Likely also for soil moisture and for soil temperature, but here we neglected them.
All right. Thank you. So you showed that ECLand can be emulated quite well, right?
Yeah.
So with different approaches. Could one now extend this approach with transfer learning and maybe take all sort of observations into account, like eddy covariance towers and other observations? Would that be possible? Could you extend your approach?
Yes. Yes, we could extend this approach, and yeah, actually, if I had more time in my PhD, that would be one of the first things I would like to do. I mean, we started now with the soil variables. This transfer learning approach could already be applied to the soil station data here. So we do have some, or there are some data sets that are already hybrid in the input data, and we would have liked to start fine-tuning and at least nudging our networks to the station data as we have it, and then even start including observations as input forcing. So this would be for the soil variables, and because as they are, this would be one of the first next steps. But yes, then also with the flux data. So as we plan to develop ECLand for more variables, and also predict the net and the gross primary productivity. Yeah, improving these emulators with observation data is definitely an option, and I would be very curious to see how far the emulators then get compared to the physical model.
All right, thank you, Marike. Then you already have a good plan for your postdoc.
I have ideas, yeah.
Okay, we have another question coming in from Matt Fry. So he or she says, thanks for the great talk. In your slide comparing GPP against different parameters for the models, many of the machine learning models didn't show GPP going to 0. Is that a problem? And does it say anything about the other models?
I believe, let me get back to the results. Was it this slide or more this with the GPP? No,
so
but because this was the error, or?
Yeah, it's GPP against the different parameters. So this one, yeah. Or different variables. And then it's so the question is that many of the machine learning models don't show GPP going to 0. For example, as we see it maybe
Okay.
in the two last plots, where
Yes.
the pre-less is 0 and the GPP model in the GPP in the machine learning models, they don't go to 0. So is that a problem? And what does it say about that?
No, because this doesn't show in the classical sense, this doesn't show the predictions, but what we look at here is the effect of the input variables on the predictions, on the prediction of GPP. And we do this marginally in a sense. So we fix all the other input variables at their mean. So this setting is artificial to start with. And we're basically interested in the functional shape that we see and not so much in the values. So that they don't go to 0, I would say could just be a matter of the time. So we're also looking here at a very specific time period, and that is during the growing season. So that could be caused by the variable importance analysis during growing season. Yeah, so that could be an explanation for this. But as we see, for example, only like a constant something like a constant function, as we see in the last plot here for the photosynthetic active radiation, that tells us more about the effect of the variable at this specific time of the year on GPP. If that explains the question.
I hope it does. So for me, at least, it was very, now I could follow very well now what your plots show. Then maybe I would have another question. So you showed that ECLand is a lot faster than ECLand. So the idea is probably also that on the long term, you would implement it in the whole IFS system, or you would at least maybe test it. So is this in terms of technical, so in terms of the engineering that is involved in that, is it easily feasible to build in your work now in the IFS system? And if so, what would you expect?
So I was told that it is not easily implemented, and so the coupling of a machine learning approach with the IFS is not easily done. I was told that this is a very tedious step, so I see that I see why not a lot of people are going this way. I also not sure if that is the way that the center, the ECMWF, is it's going to take. So they have the AIFS. If you have maybe heard about this, yeah, which is an AI-based weather forecasting model, and the land surface already plays a role in the AIFS. If the land surface parameterization will be part as a parameterization of the IFS is, I think, not clear yet.
All right. And so you showed that in the energy balance, you have feedback between land and the atmosphere, right? The lower level of the atmosphere. So now you train your models only on forcing, and that you don't have a feedback, of course, from the land.
Yes, that is correct.
To the
Yes.
atmosphere.
Yes.
So how do you think your results would be different if you would include somehow this feedback that that more evapotranspiration, of course, influences the dryness of the air, and then you have a feedback back to the land. So because you only now work on the offline land model, and if you then, so maybe you can elaborate a bit on this.
Yeah. I mean, right now, because the offline, because we're working with an offline simulation of ECLand, and we're emulating an offline, so our emulator is offline and our simulation model is offline. Just from the results that I have, it's hard to say that we, how these emulators would perform for the coupled simulation. However, I assume that with the coupled simulation, we have more complex processes because, because there are different. I would assume that there are different, energy, water, and carbon balances that need to be kept in interaction with the atmosphere, so that at least the physical model needs to fulfill. And these constraints, just as we have them here in the as raw emulators, they are not implemented yet. So when it comes to the feedback with the atmosphere, I assume that constraining the emulators more to really predicting within the within the carbon balances or the energy balance equation that I showed earlier, may be necessary to get a robust interaction.
All right. It will be very exciting to see, or it would be exciting to see how it works in a coupled system.
Yes, I agree. It would be really exciting. Yeah.
All right. So there are no further questions from the audience, and also you answered all my questions. Thank you so much. Then, good luck with wrapping up your PhD. You did wonderful work.
Thank you.
And then I thank everybody for the attention, and thanks you again for the nice talk and for also answering all the questions. And then
Thank you very much for the moderation.
Then I wish everybody a nice evening or a nice day if you join from the US. And then see you next time. Thank you so much.
Bye-bye.
Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.